Having gone over the structure of muscle, I now want to talk about the ability of muscle to produce force. And we're going to talk about that in relation to this model of individual sarcomeres that we have over here. But do remember that for arguments that are detailed in, I think, week 10, it's perfectly reasonable to talk about the force production capabilities of an entire muscle as if it's just one gigantic sarcomere. So, we saw in the last video and in previous weeks how muscles can relax and can change their length by the sliding of the actin filaments right here relative to the myosin. So we could think about the force production capabilities of a muscle as a function of how stretched out or squished down its sarcomeres are. So before we talk about producing force in an active sense, the most simple thing we can talk about is let's just assume there's no electrical signal going to the muscle at all, meaning there's no calcium getting dumped out of the sarcoplasmic reticulum. So there's no cycling of myosin heads on the actin and so on. What happens if you just stretch out the sarcomere? So if you go from this and you just kind of pull on it on either end, and you go to this. Well, it's going to behave just like, say, a tendon, where below some length it'll be slack, just like a rubber band that hasn't been stretched out enough to start producing force. And then after a certain length, these titin proteins will start stretching out, and just like a rubber band, they will produce a passive force. Maybe I'll label this passive. They'll produce a passive stretching force, right? That will have a tendency to want to contract the muscle back together. So this is the passive force length curve of muscle. And the beginning of force production here happens at a very special point that is the same as the what we're about to talk about, which is the active force length curve. So we'll put a little asterisk there and come back to it. So we could go back to this sarcomere, and now let's say we supply a big electrical stimulus. Right? We zap it with a bunch of electricity, or we provide a full capacity excitation from the central nervous system. And we examine the ability of the muscle to produce force when it's at different lengths. What we get, if you recall, we get a curve that looks maybe like this. Let's see. Looks like this. Well, technically we get a curve that looks like this. But, of course, the green line here is because we will also start getting those passive forces starting to get added in. So what we generally do is we just subtract off the passive force because we've measured it already. So this active force length curve, oops, let me get the right color here. This is the strongest piece of evidence for this sliding filament model of muscle, because it very well describes why you would get a bump-shaped force production capability of muscle. There's some length of the sarcomere where the actin and myosin filaments are optimally overlapped, so where every myosin head is close to an actin filament. Whereas if the muscle gets too stretched out, you get some myosin heads that are stuck out here with nothing to grab onto. And if the muscle is too short, then either the actin filaments overlap and block the ability of some of the myosin heads to grab onto actin, or the myosin heads actually bunch up at the end and kind of squish around. So you would expect this some optimal amount of overlap between the actin and myosin filaments. And whatever that optimal overlap is, we have a special name for that, and we call it the optimal fiber length. And it's very interesting that that optimal fiber length happens to coincide with the length of the muscle fiber at which the passive forces start to become a factor. And we generally plot this force length curve as a fraction of the optimal fiber length. So it's like 1.0 is defined as the optimal fiber length. Of course, that's where the force production capability is the greatest, and that's a special name. That special name is the maximum isometric force production. So maybe I'll write max isometric force. Isometric because in all of these experiments, we're assuming that the muscle isn't moving when we make this measurement. So we stretch it out, we hold it still, then we zap it with electricity, see how much force it produces. Then we try that again at a different length. So that's the maximum isometric force. I think we had a special symbol for that. It was this F naught. We had a special symbol for this optimal fiber length. It was this L naught, like this. On the exam, I'll specify what I'm talking about. I won't just throw symbols at you without explaining what they are. And then we also we denote all these forces as some fraction of this optimal muscle. Optimal isometric force. So this is active and passive, and then I guess you could also consider that green curve that we talked about, the total force length curve of muscle. There was one other thing that we learned about, which was there's a few other things, but one other important thing vis-a-vis these properties is the force velocity curve, and let me talk about that in another video.